No, that's not what I need. Let me see how far we got with gases last time. Got it, okay. Don't need that. This one I need. Alrighty. We have a couple more things to do with gases, which are going to involve mixtures of gases as well as a couple more vocabulary things, and then finally with kind of how we correct for non-idealness in gases. So let's start with our let's say our terminology. So effusion, just vocab time. Effusion is gas leaving through a small hole. Or gas entering through a small hole. Either way would be effusion. Actually, let's say entering. Though we'll just put both. This would be why balloons deflate. That is a process of effusion. If you have, there's your balloon. That looks weirdly like an sp3 hybrid orbital. And let's say you've got hydrogen in here. That hydrogen will leave throughout little holes in the balloon, little pores in the balloon structure. And over time, you'll be left with your very sad, floppy balloon thing left over. And guess what? Effusion rates are exactly the same kind of... the comparison could be the same between effusion rate as well as root mean square, speed, or anything depending on whatever you're looking at. And we're going to see that we kind of have the same thing here that we saw last time. That your effusion rate, if you're comparing two different gases, is it's the same idea about... Exactly. So because they're moving faster, they're going to effuse faster. Yeah, so it's the same idea. So it's the same exact equation, except we're using R instead of U. So nothing really scary there. So you're going to see that small gases will effuse faster than large gases, as Kevin has said, because temperature is related to mass as well. So your smaller stuff will move faster. And as a result, your balloon filled with hydrogen is going to deflate the fastest. So if you were to compare, say... Let's go ahead and see what the how much faster SF6 would be. Or rather, hydrogen. Just kidding. So whatever the rate is, we can just find the proportion of them. Let's see what the mass of SF6 is going to be. It is 146. And hydrogen, of course, is 2.016. So 146.06 divided by 2.016. Square root that thing. Is going to be 8.51. So that means H2 effuses 8.51 times faster than sulfur hexafluoride. So if you were to have a balloon filled with each of these gases, the hydrogen balloon would deflate 8 times faster, 8.5 times faster than the other one. And this is true if you see a balloon of SF6, that thing just sticks around forever. It's a very slow-moving gas, so the balloon will stay inflated for a very long time. Fun fact, that balloon is also really, really dense. The balloon will feel heavy. It's really bizarre. We're used to balloons just, floating away, and we never see them again until they kill a turtle in the ocean or start a fire or something. They crash into power lines. But yeah, balloons full of sulfur hexafluoride are actually really heavy. Another fun fact, hydrogen, like helium, will make your voice super high-pitched and squeaky, whereas sulfur hexafluoride makes your voice really, really deep. And it's just all related to the density and how pressure moves through various media. So, cool. Fun stuff. Alrighty. Cool. Nothing really new there, so no need to really do more examples of that. It's really the same thing as before. So just one more thing to remember. So we saw that the root mean square speed was 3R. No. 3Rm over T. Oh gosh, now I can't remember. Yeah. Is it okay? Let's just double check. This is not something I ever do outside of this class, so let's just double check that I have the right formula. I'm not cheating, I promise. No, RT over M. Okay. Alright, nobody saw that. Oh my gosh. Perfect. Okay. And then it turns out the most probable one is a very similar formula. So, in case you ever need to look up calculate the most probable speed of something, you can use this equation here. All right. What does this tell us, by the way? We already know this, right? We know this is always we know that root mean square is the fastest of those three speeds we looked at, right? Most probable is actually the slowest one, and in between them we're going to have our average. So you can calculate them if you want to. Very exciting stuff. And so we saw, I think, last time that we had some gases that were traveling at like 500 meters per second. Totally is a normal speed for a gas. But they actually are not typically covering that like lateral distance in that amount of time, because gases actually collide all the time with each other. So a gas might effuse into a vacuum or whatever speed it's going on, at its speed, let's just say. Where there's nothing in the way to get out of there. So it can move really quickly. It just goes from one end to the other, no problem. However, diffusion, which is gas or liquid or whatever, it's going to move into an area with lower concentration but not a vacuum. diffusion is much slower than effusion is. So effusion, things just leave into like an empty chamber and poof, they're there. It's nice and easy. Diffusion, though, which is things just kind of spreading out into an area that is not completely empty, is a lot slower of a process. The reason for this is gases, they usually will have about 10 to the 10 collisions per second. That's a lot of collisions, right? That is 10 billion collisions per second. So these gases are constantly bonking into each other all the time. They're traveling very, very quickly. And as you can imagine, the more of them there are, like, you're going to bonk into each other very, very often. And so this, since these gases get deflected when hit, they overall have a small mean free path when diffusing. So effusion might be something like this. We have our box with all these lovely gas particles inside. We open a small hole. We don't destroy most of the box. There's a small hole. Now this gas molecule can just go crazy and go all the way over the place. No problem. However, if we are going to do this same thing, we have a container that has some gas in it, and we are going to release it into an area that already has a ton of gas. This one might hit this, then go here, then go there, 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 then there, bump, bump, bump. As it hits everything, it just keeps being deflected in all these different directions. And so, it's going to keep just moving and colliding with things. And eventually it might reach all the way over here, but it will have traveled a lot more distance. So overall, it doesn't look like it's traveled very much. Its displacement is low, but its speed is going to be exactly the same as it was if it were effusing. So, but it's being deflected around, and so as a result, it can't travel in a straight path. So we're going to see that something like flatulence or perfuming or perfume spraying or whatever, those things are essentially a diffusion process. So some odor is released by this naughty dog over here. I see you, mister. Or by someone's children or whatever, or by you, whatever. It eventually will be able to be, smelled by everyone, right? Someone in the back of the classroom spraying perfume. Eventually it will reach all of us. So we might calculate a perfume, traveling at a speed of 400 meters per second. That would tell us essentially as soon as it's sprayed, we would all be smelling it. However, because those perfume molecules are bonking into every other molecule around, they take an actually long amount of time to cover a reasonable amount of distance. So that's the lesson here. So we're going to see that on average, you don't need to know this number, but gases travel about 60 nanometers per second in real life as a mean free path. Whereas we saw, 500 meters per second would be if they were just going plain old effusion into a vacuum. And so we're going to see that you can see this is about a 10 to the 10 difference in how fast things are moving. So that's why it takes a couple of minutes for the perfume in the back of the room. Yeah, this is about 1 atmosphere. If you were to go to like the edge of the stratosphere or so, if I remember correctly, it's like 10 centimeters per second or something. So that even, at pretty low pressures, you're still got a shorter path. So again, these are not numbers you need to learn. This is just to illustrate to you why these things are happening. Okay, so there's our vocab lesson for the day. So, yes. Cool. Alrighty, so with that in mind, we kind of have 2 more topics to deal with. We're gonna, effusion is the first one. And this is diffusion. So effusion, technically effusion and diffusion are kind of the same thing, but diffusion, what would be the best way to... Okay, so effusion is something moving into an area that there is none of it already. Diffusion, there could be. You could have stuff already there. So, that's more the idea. So, effusion is typically something that doesn't exist in real life, because it's not really possible to get a perfect vacuum. Yet, like, things can be moving out, they're not moving in. Diffusion is kind of a things moving all over the place kind of idea. Effusion one direction, diffusion all over these directions. So, that's the thing. Cool. So if you think about the balloon example, if your balloon has hydrogen inside of it, there's not really hydrogen in our air around us. So it's effusing out of that balloon. And then it is diffusing through the air to whatever. So yeah, there we go. Cool. I know, very exciting. So it's a really fine line between them. So just kind of understand effusion is one direction, and it's usually into an area that there's nothing there. Or a very strong vacuum or something, or there's just none of that particular component there. Diffusion could be anything. Alrighty, especially if you talk about biology, you'll be talking about diffusion all the time. You'll have concentration gradients, sodium outside the cell, inside the cell, causing voltages and blah, 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 fun bio stuff. Cool. Let's talk about a few kind of constants we can calculate. One of these is going to be the molar volume. And that is going to be the volume that 1 mole of gas occupies at a particular temperature and pressure. For archaic purposes, way back in, the 1800s, when people were actually doing these experiments, they had a set of conditions called STP, which was standard temperature and pressure. And they would be doing all their gas experiments at these standard conditions so that people would have a kind of clean slate to compare against. So if you're only changing the volume or the moles, you can see if standard pressure and temperature are the same, it makes it easier to calculate stuff and easy to observe changes. For a long time, that was defined as 0 Celsius and 1 atmosphere. In the 80s, that was actually changed to 1 bar. I think this was 1987 or something. However, nobody does that. People still refer to STP as the old way. with atmospheres. So even though it's been, almost 35 years or something, people still use the old definition for STP. So let's go ahead and see what the molar volume would be at STP. That would be 1 atmosphere. So V equals nRT over P. We're saying we have 1 mole, 0 degrees Celsius, and 1 atmosphere. So 1 mole, 0.08206, 298.15, 1 atmosphere. You do this, you get 22.4 liters. And this is a magic number that will allow us to do things if you are at STP, if you are doing a problem that uses standard conditions. This is a handy number for us to have. This again is the volume of 1 mole gas at STP. Remember, since this is the ideal gas law, all the gases are the same, so any gas we could apply this for. And so this actually gives us a conversion factor that we could use to solve for things. That's Kelvin. So remember, I'm sorry, 273.15. You're absolutely right. My bad. I'm so used to using 25 degrees, that's why. So yeah, 273. Good catch, Kevin. So 22.4 will be your magic number there. If you use the bar definition, you get 22.71, but we're going to stick with atmospheres for now. So let's go ahead and work with this. By the way, 22.4 liters is approximately 1 cubic foot, thereabouts. So just so you know, it's like a cube of, roughly those dimensions. I used to have one that would show it, but COVID. Alrighty. So this is just basically a shortcut for us to do. We could totally plug all this to the ideal gas law. We would get our answer, and we're done. However, this is basically just a little shortcut. We can get rid of temperature and pressure and do things a little bit more quickly. So we would set this up. We would use, of course, our molar mass, which is going to be 16.04. Yeah, that sounds right. We would be able to do this. Let's go ahead and do the calculation. 28 divided by 16.04 times 22.4. And that is 39.1 liters. Hooray. So, for something like this, again, you could use ideal gas law. You would get your moles from doing the molar mass. You would then plug that in. V equals that number of moles times RT over P. Okay, but just saves you a little bit of time there. We can also use this, by the way, to make another equation. If we look back to way back when, we had density, right? Density was the ratio of the mass to the volume. And we could also use the ideal gas law to figure this out, or we can just use some fancy tweaking. How do we relate mass to moles again? I don't remember. Yeah, right, molar mass, right. The moles times the molar mass equals the mass, right? That's not a mu, that's a... I'm trying to make that fancy M from before. Molar mass, I'll just write that. And so we could say that the density of a gas is the moles times the molar mass over the volume. If we take a look at our ideal gas law as well, if we wanted to kind of isolate N and V, we could do that. And so, by substituting in N over V, we can get P times your molar mass over RT. Hooray! So we can calculate the density of a gas by using a formula. Again, you could use just plain old ideal gas law and do it the old-fashioned way, you know, solve for a volume of 1 or something and do it that way. But yeah, that would work. So we could find what is the density let's go back to our chlorine. Oh no, we did chlorine, huh? We're at the beach with our chlorine gas. And what did we have it at? 150 degrees? Been a long time since we were at the beach conducting our chlorine experiments. We could figure it out using this equation. Again, you could use the ideal gas law. There's no need to necessarily memorize this equation or anything like that. You could use the ideal gas law to understand that density is in, if we do it in grams per volume, you could solve for moles for 1 liter and then convert that in moles into grams. That would work just fine. But equations make people happy, so let's just do that. So 1 atmosphere molar mass temperature 150 plus 273 423. Let's go ahead and look at our units. Atmosphere should cancel. Moles will cancel. Kelvins will cancel. We are left with grams per liter, which is a density, right? That's a mass over a volume. So doing this, 70.9 divided by 0.08206 divided by 423.15. Doing this, I got, oops. Hooray. Notice that since temperature is in the denominator, awesome. Yes, I got it, Kevin, too. We both got it. That means we're both right. No need for Tyler to come in and prove us wrong, as always. Just to put this again. We see that density will increase as temperature decreases. And the opposite is true. Exactly. So I guess I wrote the opposite as Kevin did, but they're both true. The converse is true as well. So you're going to see that colder gases are more dense, hotter gases are less dense. And we're going to see that that's how, hot air balloons work. Dense stuff likes to settle down to the bottom. And so less dense stuff tends to go to the top, like oil floats on water because oil is less dense than water is. It's a way of kind of making gravity happy. So more dense stuff sinks, less dense stuff rises. So coldest spot in your fridge, what is it going to be? It should be the bottom, right? That's where the most dense gas would be, which would have the lowest temperature. So the lowest part of your fridge should be the coldest. There may be different, pumps and stuff making it equilibrating, but if that were the case, that's what it would be. So that's why you have if you have ceiling fans, you have that switch to make the fans go the opposite direction, so that in the wintertime it actually pushes the air from the ceiling downwards. And so that's going to move the warmer air down towards you, whereas in the summertime you're doing the opposite process. So you're just forcing air to move, trying to move the hot stuff out of the way. So yeah, good stuff. So notice pressure is also part of this. And so we're going to see higher pressure means higher density as well. And that should be self-explanatory because density and pressure, volume and pressure are inversely related. So we would expect density and pressure to be directly related. Woo, exciting. All this fun stuff. What the heck do we do with all this information? It's a good question. Whatever you like. The gas stuff is, again, it's mostly old chemistry, but occasionally it is of interest to still do experiments with them. Cool. Alrighty, let's talk about mixtures of gases. So these are kind of just like the trail end things. We've talked about most of our gas stuff already. We're kind of learning just a few other applications here and there. So we can talk about mixtures of gases. So some gases you'll have as pure substances. They'll just be, a tank of oxygen gas or whatever, or your fire extinguisher full of CO2, whatever it happens to be. But you may also have mixtures of gases, like an important one called air, that perhaps we are familiar with, which, as we might remember, follows these proportions, not silver, argon. These tell us that 78% of all molecules in the air are N2. Get at what? 0.093? I thought it was 1%. To the Google. I see 0.93%, which is roughly 1%. I think you've got an extra zero there. So yeah, so it's technically 0.93%. That's roughly 1%. So of course, because you have other things in there. You have water vapor, you have carbon dioxide, you have methane, you have chlorine gas if you're at the beach accidentally spilling it out everywhere. There's tons of other gases, sulfur dioxide, all sorts of things. So I just round that to 1. But yes, technically it's 0.93. Not 0.093, but 0.93. Okay, cool. So these are reported as what are called mole fractions. And so we're going to see that we have these percentages are not percentages by mass or by volume, but they are by they are called mole fractions. So this is telling us that the moles of N2 over the total moles for air is 0.78. So this is a mole fraction, which is given the letter X, capital X, is mole fraction. And so that's going to be a mole of one particular substance over your total number of moles. So for oxygen, I guess I should be consistent. That's 0.21. That's how we get 21%. So percents for us in gases are always going to be given in mole fractions, unless otherwise stated. And we're going to see that because all these things relate to moles with our ideal gas law, we have another important fact here. Each gas in a mixture exerts a pressure proportional to its abundance. That would be mole fraction. So we're going to see that at 1 atmosphere, sea level, we know that we and we have 78% nitrogen gas. This tells us that N2 exerts 78% of the total pressure. And we call this the partial pressure of nitrogen in this case. Get ready for this complex math. There's our total pressure and our mole fraction. Let's see if Tyler can do this one. Mole fraction does not have a unit, by the way. Wow. So thankfully for us, because normal, atmospheric pressure is 1 atmosphere, and since nitrogen is 78% of the air, nitrogen is 78% of the total pressure, so nitrogen's pressure would be 0.78, just like its what am I trying to say? Percentage. So here's a formula for you guys. Easy formula. Your pressure, your partial pressure of gas A, whatever it happens to be, is going to be equal to the total pressure times the mole fraction of A. Remembering that mole fraction of A is the moles of A over the total moles. How exciting. Another way to write this sigma notation, everybody loves this. The total pressure Oh gosh. Well, I don't know what our thing is going to be, whatever these happen to be. But the total pressure is just going to be equal to all the pressures of all of your gases. So, kind of obvious, I guess. What we're saying here is that 1, 2, 3, 4, 5, 6. Is that 6? Yes. And 3 here. Let's just say, let's say this is 1,000 torr. This one should be 500 torr, right? It's got half as many molecules, so therefore half the pressure. And so this one that's got them mixed together would be the combined one. Very exciting, very difficult math here. So if you add up all of your partial pressures in a mixture, you will get your total pressure. And this one is actually going to be important for us because in real life, when we're trying to isolate gases, the best way to do it is to collect it over water, rather the easiest way, not necessarily the best way. And so we're always going to have water vapor as part of our mixture of gases. And so gases that are collected over water might look something like this. So you've got some container, you've got your gas collection bottle that is completely full of water, and it's upside down. All right, completely upside down, so it's completely full of water. What you do here is your reaction vessel. You're going to have a hose essentially connecting these two. And so the gas particles are going to come up and go into that bottle, and it's going to push out all the water as it begins filling with gas. And thankfully, because of gravity and how vacuums work and all that fun stuff, we're going to essentially end up with, we have all our water here, we end up with a tube upside down completely filled with gas. The gas that we're interested in. Maybe there's still some water in there, depends on how much gas you're producing, but you'll end up with a tube or a container of gas. So let's say, maybe we had a reaction here. Oops. We're producing hydrogen gas, maybe. All that gas is going to go in and push out the water, and now we will end up with a bottle full of hydrogen gas. In reality, though, some water vapor will also go in. And this vapor has a known pressure at a given temperature. Swapping to Discord real quick. Ho, let's have a look here. Look what I did for you guys. Not van der Waals. Look at this lovely table I've got for you. So, whatever temperature you are collecting your gas at, you're going to have a contaminant of water vapor that will exert a particular pressure. These pressures are pretty small. As you can see here at normal temperatures, it's, not even close to an atmosphere. These are given in millimeters of mercury on this particular chart. However, as your water is heating up more, you're going to end up with more water molecules in the gas phase. And as you can see, as you get to water's boiling point, the vapor pressure of water is equal to 1 atmosphere. Exciting. That's something we'll learn about next chapter, but remember that for later. So, essentially, for your homework problems that deal with things collected over water, you're going to have to take this vapor pressure into account. Shall we do something like this? I think we should. Let's take a look at what a problem might look at. Oh, the atmospheric pressure is, we're going to be in a high pressure system today. So atmospheric pressure does vary depending on weather conditions. Some days it is lower, some days it is higher. High pressure typically is going to be hot weather. Not a lot of storms. Low pressure is when you get rainy weather, humidity, or thunderstorms or that sort of thing. Or actually not even thunderstorms, that's rain really is typically low pressure systems. So, but that's meteorology, that is not this class. So, let's really go crazy with this problem. Will this problem work? I wonder if this might be too difficult to throw at you guys right away. It probably is, but let's do it anyway. How exciting. Let's what the heck is happening here? Oh, I didn't give you guys a reaction. Okay. So, woof. Exciting things to learn here. Remember that the pressure outside of your gas container will be the same as the pressure inside. We essentially are using a manometer type system where we're going to have a little bit of water that's kind of our, like, blocking that off. But essentially the atmospheric pressure that's pushing down, and you've got the pressure of the gas pushing down on the water there. Man, this might be just too complex for you guys, but we'll do it. Suffice it to say, they're going to be the same. Okay, so that's how physics will work here. So we're going to make it so that they're going to be the same because our water levels will be equal. Cool. I really regret choosing this problem, but let's do it. So, let's have a look. Pressure outside is going to be atmospheric pressure, right? Which I've told you was going to be our whatever 764. I gave that to you. This is going to be equal to the pressure of the hydrogen plus the pressure of the water vapor. We could look at our table to see what the vapor pressure is of water at this particular temperature. If we do that, we see that our pressure is going to be, looks like 19.8 torr, millimeter of mercury torr, same thing, remember? So let's go ahead and have a look here. So the pressure of hydrogen will be equal to 764 minus 19.8. So that would be 744.2 torr. Okay, and so this is specifically hydrogen. That is the partial pressure of hydrogen itself. Let's see what the heck other information we have here. So we have a temperature. We have now a pressure of our hydrogen. We don't have a moles, but we, by the way, we're calculating the volume, so of course we're not going to have volume, right? Let's look at this zinc thing. Is there any way we can get moles of hydrogen from our mass of zinc? Yes, there is, right? Stoichiometry has never left us. So we have pressure of H2 now, and we have temperature. We need a moles now before we can calculate our volume. So, shame on me throwing you guys into all this stuff. But you thought you could forget it. That's not allowed. What's our molar mass of zinc going to be? Zinc has a molar mass of, where did it go? Where the heck is its molar mass? Oh, there it is, 65.38. Okay, awesome. Let's look up at our chemical reaction. For every 1 mole zinc, we get 1 mole of H2. Alrighty, so really we just have to do 5 divided by 65.38. And apparently Kevin already did that for us. Kevin, why did you get twice as big as what I got? Did I balance this incorrectly? 2 hydrogens, 2 chlorines, 1 zinc. I got half of your answer. What did you do differently, Kevin? Oh. Is that grams you've calculated? Oh, okay, gotcha. We don't need that. Because we're looking for volume. I guess you could use the density to figure out the mass, or the volume. That would technically work. Go ahead, do that. Let's see. I was going to use the ideal gas law, though. Which is essentially the same thing as using the density, but keeping it as moles, I think, is a little bit easier. So, volume. Moles times R times temperature over the pressure of hydrogen. 0.0765. 0.08206. What was our temperature? 22? Wow, what a complicated problem. 295. And the partial pressure was, oh my god, I didn't convert it to atmospheres. Shame on me. I'll just put it in. Sorry, my bad. Hooray, look at all this crap we can do with these gas laws. We can throw all the stuff we thought we could forget. Already. So, oh wait, did I? Hold on. I forgot to put a parenthesis in there. Parenthesis, rather. Okay, so doing this, I get 1.89 liters of our hydrogen gas. That's going to come out there at this particular temperature, at this particular collecting over water idea. I'm going to draw a very sad face. Long problem that. Took us almost 10 minutes. Let's start with an easier problem tomorrow, I think, for this idea of mixtures of gases. I think I moved a little bit too quickly here. So I apologize for that, but tomorrow we will continue with more of this fun gas stuff. And then we have one more equation to learn, which is when we're going to bring in kind of real life to these ideal gases. And from that, we're going to need the second table in our in Discord, but right now just that first one will be sufficient. So, woof. Okay, I will post your homework today. It'll be due Sunday, because your exam on Monday does not cover gas laws. So it'll be just due on Sunday as normal. Though I still may post the key some other time. So yeah, cool. Exciting. Do we have questions on this? Out of curiosity, Kevin, if you use your mass of hydrogen and you tried to use the density, you got it. Okay. That's the density of let's find out if we get the same thing. And so you calculate what, like 0.154 grams over a density of 0.0816. Let's see if that works. Oh, look what you get, 1.89. So Kevin's extra steps did get him the same answer, which is good. So, did that feel like extra steps, Kevin, out of curiosity? Because I guess you would have had to use... I mean, if you're going to use this one, you didn't feel like it? Okay, well, there you go. That's one way to calculate this problem as well. So, yeah, you still just have to do the ideal gas law once, I guess, and that's it. So, cool. Well, either way works. Best part about chemistry. Okay, so before we go, I'm going to also be posting up the description of your lab project, as well as some videos that you guys should watch. What I want you to do this week is start thinking about teams. So you'll be in groups of 4. I don't know how many students we have in class. I think it's probably, I don't know. But we're shooting for groups of 4. If you have anyone you would like to be with, and that is consensual, by the way, not everybody can say, hey, I want Kevin on my team. Um, you know, if you want to make your own groups or say, hey, I want to be with, Tyler wants to be with Kevin and they need 2 more members, then I'll just assign them randomly. That's fine. Or if you say, hey, the 4 of us want to be a group, that's fine too. You want to let me know by the end of the week for that, because I'm going to make our fake, or I will randomize the groups on Friday based on the information that I have on Friday. Okay, and then next week you're going to be given a problem, and we'll work through it together. So with that, I'll be posting up the thing today. Yeah, so I guess submit your bribes to Kevin as soon as possible so he can make the choice of who he wants to work with. And yeah, so it'll be exciting. So I'll post the description up. Go ahead and take a look at it. And and we'll see how that's going to work. So this is my first time doing it this particular way, so this may be a complete disaster. If it is, we'll move accordingly. So don't worry. Like, this shouldn't be too crazy. So we'll see. Okay, so look forward to that later today, as well as your homework for this. So see you guys tomorrow.